कर देना था स्टार्ट। एक मिनट और वेट कर लेते हैं। A very good afternoon to all of you. Am I audible, sir?
Hello.
Okay. So let's move ahead with our second session. And for this session, we have Dr. Hemant Saxena from dSPACE Solutions. Dr. Hemant Saxena is serving as Field Application Engineer at dSPACE India Solutions, where he specializes in e-mobility domain. With over 4 years of experience spanning both industry and academia, Dr. Saxena brings a wealth of expertise in rapid control prototyping and hardware-in-the-loop testing, leveraging a wide range of dSPACE hardware and software solutions. He holds a PhD in electrical engineering from Delhi Technological University, where his research focused on the application of power electronics in power systems with PV integration. During his doctoral research, he developed prototypes for single-phase and three-phase grid-tied PV systems. He has a strong publication record with over 16 research papers in reputed SCI journals and have presented his research at IEEE national and international conferences. So I welcome Dr. Hemant Saxena for our program, and I request him to start his presentation.
Yeah, thank you, sir. Am I audible, sir? Hello. Am I audible? Hello.
Sir, थोड़ा सा प्रॉब्लम आ रही है. I think we are not able to hear.
Hello. Hold a second. Hello. Am I audible, sir? Okay. Sanjeev, sir, am I audible? Because other like attendee is saying, yeah, I am audible. Deva, sir, am I audible to you?
Sir, can you share your screen? Let's check first.
Okay, hold a second. Okay, my screen is visible to you?
It's visible, but there is some.
Audio is not coming? Hello. Yeah. Okay, Deva sir, or anyone can like unmute yourself and like, maybe you can say to us.
Yes, sir, you are audible.
Okay, okay, great. And voice is coming good quality, right?
Yes, sir.
Okay, great then. So I am going to start. So thank you, Sanjeev sir, and thank you, Deva Prasad sir, for inviting me for this session. And
हेलो।
thank you for, yeah, hello, hello sir.
हाँ सर, आवाज़ नहीं आ रही आपकी।
Okay, maybe I have to remove my headphones.
हाँ ठीक है, अभी ठीक है सर, ओके। हेलो।
How now, sir?
हाँ अब ठीक है।
Okay, correct, great then. Okay, thank you, sir. And okay, I'm going to start the session with the like you can see the dSPACE logo. So I am working here from past 3 years and serving the customers like an academic customer and the industry customer for the RCP and the hill testing. Okay, first I will talk about the dSPACE. So you can see we are like partner in simulation and validation. So maybe anyone who heard about the dSPACE. So it's like a digital signal processing and the control engineering. And today's session will be like a dSPACE-based real-time simulation for power electronics tools and application. So I will discuss about the what are the challenges during the real-time simulation related to the power electronics and power system also, and what are the tools which is required from the dSPACE side or the any third-party side so that we can do the RCP or hill testing or any real-time simulation. Okay, so from this title slide itself, so real-time simulation. So there is a what is a real time and then what is not real time. So not real time, like which is not synchronizing with the time and the real time, the like nature time, and those which is like synchronizing with the real time. So that is the real time simulator. So when I can give an example, so suppose that you are simulating any model in the MATLAB, and suppose that you are going to give that sample. The simulation time, suppose that 1 minute, and maybe that simulation model can run within 10 seconds, or maybe it will take more than 1 minute also. So it means the system is not running in real time. So in between, anyone can ask question, that is also okay for me. If anyone want to discuss after the presentation, that is also okay for me, and I will try to answer your queries. But if I am not able to answer some of the queries, maybe I could get back to you after this presentation also. That is like I will be happy to help you in that. Okay. So now about the dSPACE, and we have more than 35 years of experience and more than 2,800 plus global employees, and we have footprint of the regional dSPACE companies in 10 countries around the globe, and we have 4 project center in the Germany's, and we have 5 distributor companies in the other countries also. So if we come to the around the world, you can see like the headquarters is dSPACE Germany. We are spread over the dSPACE Sweden, UK, USA, France, Croatia, India, China, Japan, and Korea. And you can see that like a different color code, like false. There are some companies related to sales and engineering. Some are only for some are for development also. Some are for the production also. So in India, you can see dSPACE India. We have two things like a sales and engineering and the development also. So in dSPACE India, we have headquartered in Bangalore, and we have regional offices in Pune, Delhi, Kolkata, Chennai, and Trivandrum. So at Trivandrum, that is the development center. And currently, I am sitting at Delhi location, our office in Gurgaon. And like I have also worked with the Bangalore at Bangalore location and the Pune location. So I have quite wide experience within the dSPACE India also. Before joining the dSPACE, I have used the dSPACE system during my PhD also. So I am well aware with the academic users, how they use it, what are the shortcomings there. Okay. So now, like where the dSPACE gives solutions, like in the automotive, aerospace, commercial and off-highway vehicles, agriculture, railway, marine, electric drives, academic research, and the medical engineering. If you talk about the automotive, suppose that in North India, so we have customer like Maruti Suzuki, Mando, and like Honda, Hero Motocorp. So these are the related to automotive. So in the different part of country, we have different users there. They use our system for the RCP and the hill testing and the other solutions also. I will discuss other things also. Okay, so today's agenda will be like introduction, and the second point will be the concept of mill, sill, pill, RCP, hill, and PHIL. So like I want to explain why I want to explain, because maybe these are the very normal thing, but maybe those who are working in this domain, they are not clear about the what is mill, what is sill. So I want to explain those things. I will try to give one real-time demo for the three-phase sun-active power filter. Currently, the one device, the hardware is not available in my office. So I will take a remote our other office location and will try to explain it. Also, I will give the detail about the processor and FPGA-based real-time simulation. So like when you are going to simulate, so there will be two options. Maybe you are going to simulate in the processor, or maybe you are going to simulate in the FPGA. So we'll discuss on that also. If the time will allow more, I could discuss other dSPACE e-mobility solutions, and they're definitely their basics also. Okay. So when we think about the automotive or the related to the software or hardware software development, so the automotive basically most of the time follow the V cycle. So like in the V cycle, so the first thing will come on the requirement, then mill and sill simulation and the rapid prototyping. They generate the code, and the code can be generated and dumped into the real issue, or maybe it can be used as the virtual issue also. Then they go for the hill testing, and the mechatronic test benches or the vehicle testing. So in the left cycle, that is for the verification and or the development side, and the right side is related to the validation. So whenever we call the RCP or model in loop, so these things are like used for the development purpose, and the right side you can see all are the for the testing purpose. Okay, so testing means testing of the controller, and like development of the new function or new controllers. Okay, I will explain every each terms. Okay, so you can see one example here basically. So if you are going to do the mill simulation, so MATLAB will be used. So like that is offline simulation. For RCP system, we have like a dSPACE Scalexio based system, or the MicroLab box or MicroLab box 2. And to generate the code from the Simulink model, we use production code generation target link. And for the SIL simulation, we use BIOS, so like virtual electronic offline simulation. And for the hill, we have the Scalexio system. This is the test bench case, and this is for the vehicle testing. So like vehicle in loop system. Okay, hold a second. Okay, so first, what is the difference between the mill, SIL, and pill? So mill stand for the model in loop, and the SIL stand for the software in the loop, and pill stand for the processor in the loop. So you can see here in the model in the loop. So like for any system, there is two part. One is for the plant model, and other is for the controller model. Okay, so controller will generate some actuating signal for the plant model. This is the plant model. So controller will give some generate some actuating signal to the plant model, and this will give as a output signal as a feedback to the controller. So this thing you people usually do in the like any simulation software. So like for this presentation, I am considering MATLAB Simulink. So here both the controller and the plant will be available in the MATLAB with the like Simulink block set. When you're going for this SIL like software in the loop, so once the controller function is ready, you are going to generate the code and running the controller in the code format, and your plant model will be in the simulation by using the simulation block set. So that will be called as the software in the loop. In case of processor in the loop, your generated code has been dumped to the any evolution board, and that is your plant model will be simulated in your PC. So these things like the plant model will be simulated in your PC, and the depends upon the mill, cell or pill, your controller will run. So this is the basic difference between the mill, cell and pill. Okay. So for that I want to explain the like other points. So like what is like mill and cell simulation I explained already. So like in the RCP we are going to testing and validation control algorithm. So like you have the suppose that you are running you want to run one inverter. So inverter require the 6 PWM pulses for the 3-phase inverter, and that can be generated by any real-time system. So you are running your controller in the real-time system and your physical hardware will be there. So that will be called as a rapid control prototyping. And then production code generation. So we generate C code for the ECUs. So that is the production code generation. Still I already explained. For the hill testing, so hill is like for the testing purpose. So your controller is with you, but hardware is maybe not available with you, or you want to test your controller within the safe environment. Suppose that if so something in the voltage source converter there is a DC link issue, like high, it is maybe going to dip due to the wrong switching operation. So if you are doing with the real hardware, there will be the safety issue and it can damage your hardware. But in case of hill testing, there is no issue with the safety concern. And mechatronics test benches, so real hardware component will be there and used to provide the required input for the issue. So it's like some part will be simulated and some part will be the like emulated with the real hardware. So vehicle testing, so entire vehicle is coupled with a real-time simulation of driving scenario. So this vehicle testing is generally used for the autonomous vehicle. So like your vehicle will be on some test benches, and we can create the environmental scenario, and so that it can be tested in the lab itself. Okay. Okay, so when we come to the e-mobility, so there is some identified trend. So like increasing power density. So like previous we use switches, like silicon-based switches. Now it is changing to SiC based, and then it is changing to GaN based. So like your power electronics hardware or the switches is going to smaller in size with equal or more power. Increasing number of switches. So we are those who are working in the power electronics domain. So they're developing new topologies, and so with the new topology, there may be increasing more number of switches than the standard inverter. So like parallel and interleaved structures or the multi-level architectures. Also, while increasing the not increasing advancement in the material technology for the IGB, the switches, maybe the like for DC-DC converter, we are going to use more than 200 kilohertz, or the from drive inverters, it is around 20 kilohertz. And like the DC link voltage is increases, it's maybe go beyond the 1000 volt. Wait a second. Okay, so increasing controller complexity. So day by day controller complexity is increasing. So for that, like we have to work on the rising fail-safe requirements, fallback routines, and there is a great integration of e-mobility, like vehicle to grid or grid to vehicle. So these are the new identified trends, industry is working on those topics. Now, I have discussed like mill, seal, and pill other thing. Now we'll discuss about more about the RCP. So suppose that I am taking one example for the electric motor control. So the real environment will be like there will be one controller which will generate control signal for your power module. So it will be the like PWM signals, and it will control the voltage and the current, and then you can run your motor. So running the motor, you can detect the current and the position of the motor by using the sensors. Okay, and the measured signal will be given back to the controller. So this is the like real environment to running a motor. But now what is happening here? We are going to simulate the controller model in real-time systems. Maybe dSPACE, it may be others, but that will be called as the rapid control prototyping. So like in my experience in the academics, most of the research are using these things. So like they are going to develop new control logic, and they are testing their hardware with those newly generated functions. Okay, and like why rapid control prototyping? So like test and run new ideas and using a high performance system with virtually no restriction. Implement your Simulink state flow model at the push of a button. Get convenient access to all relevant data during the validation. So get convenient access means you can change your parameters, and you can measure your parameters through our software, and you can tune it also. So you can see here there is a two figure also. One is related to the Scalexio-based system, and the another one is related to the micro box one system. So this maybe some users have already used this system, but this is the new one, and you can see like the process is almost the same. So first you are going to simulate your model and simulate the controller model and the plant model. If it is going good, you are going to implement the controller model. Then you are assigning the channels like input and output, analog or digital. And then you are going to implement this MATLAB model to any real-time system. And then you can load to the control desk. Also control desk is our solution like the software. So for the monitoring and tuning. When we see monitoring, we are measured to measure the internal signal of your controller, or we are going to measure the whatever we are giving output, we are giving as an input to the like the system, that we can measure also. And suppose that if you want to tune, so tune anything, so that you can tune in the real time. Suppose that example like you are going to using PI controller, so there will be like KP and KI value, and you are not sure about the like which value will work. So you can change in the real time, and you can see the output of your hardware, how it is stable, it is working as per your requirement or not, so that you can see that and you can tune it also. So I hope till this slide this is okay, and anyone has any questions? So like does anyone want to ask questions related to the rapid control prototyping? Okay. So
Sir, I think we can take questions at the end of presentation. So
okay,
that
no,
will be better. Yeah.
no issue, sir, no issue. It's like in between, so that I can understand like people are
Okay.
getting
Okay.
or
Yeah,
okay,
yeah. Okay.
that's
Okay.
okay, no problem. Okay, so this is one use case, and for the rapid control prototyping, this is like you can see the hardware like for the three-phase active power filter, and we are going to develop some control algorithm. And suppose that like this is the distribution grid, and this is the non-linear load which is injecting harmonics. So how this device will help you to do this? So simply what you have to implement sensor, and you should measure the source ABC current of the source current for the all the three phases, and DC link voltage, and you are using sensor. This is very important, because suppose that here the voltage level is maybe 230 volt, DC link voltage maybe 400 volt, 800 volt, but any processor or any DSP device cannot take up to this voltage, so you have to step it down and also isolate it. And then you can give, these signals are mainly the analog signals, so you will give it to the ADC channels. Then you process your control logic, and then you can generate PWM pulses for this three-phase voltage source converter. This is different use case related to the motor control. So it's a similar fashion. So you are going to measure the voltage and current. You are going to measure the speed and position, and then you are processing your logic, and it will generate control signal for your power module, and that will control the voltage and current for the motor for the optimal operation as per your requirement. Also, when your laptop, your PC can be connected to the micro lab box for the monitoring and tuning purpose or the controlling purpose, and also to do the channel assignment. So like different channel can be assigned as per your requirement. Okay. If we talk about the different products related to the rapid control prototyping, so like there are different products here. So like there is in vehicle, there is some product, maybe the in vehicle application or maybe the laboratory purpose. So those which is used for the laboratory purpose, it is can be used on the tabletop. You can give the supply to 230 volt, but those which is used can be used in the in vehicle. So that maybe it will work with the 12 volt, 24 volt. So what are the voltage level available in your automobile? And those are very rigid, so that can withstand different the vibrations also. Okay, so these are the like some. Okay, so these are some features. So in vehicle and laboratory use, variety of interfaces, flexible PWM generation or the high PWM generation can be done. Powerful FPGA are there, so that you can do the like by the very small sample time, signal conditioning and power stages, and the comprehensive software support. So software will be adequate to do all your operations. So if we see the different hardware and software, so like there is a thing. So like for the hardware side, we have real-time hardware, and for the signal conditioning, we have Rapid Pro hardware. So the like voltage range is 6 volt to 30 volt, and it can go up to the 60 ampere current. But yeah, if you can stack it for the larger voltage and current range. For the software side, we have implementation software related uh, to manage the I/O channels for the like suppose that the encoder is generating A, B, and G pulses, and that can be given back to the um, our real-time system, and that will convert into the position and the speed, and also XSG AC motor control library and the XSG utils library. So these two libraries are provided for the implementation in the FPGA cards, and this implementation software will be used for both the processor and the FPGA. Now the RCP part has been completed. Now what is the hill testing basically? So if you will come to the like real environment, again that is a similar thing, but this time you are going to simulate the power module, simulate the motor module, simulate the sensor module, and your controller will be real, so that you can test your controller, the final controller, and the like product ready controller without any safety issue as per your desired test conditions. So for that, we may use a Scalexio or the other hardware also. In this photo, I have seen the Scalexio one. So Scalexio one is basically, it has one processor card, and you can put different cards. Different cards means like it may have different I/O channels, it may have the different communication channels. So it depends. So Scalexio means the scalable input or output. So you can increase the number of channels as per your requirement. Okay, so this is the Scalexio system. This can be used for both rapid control prototyping and the hill system. When the Scalexio is used for the hill system, it will generate the sensor signal which are required by the controller, and it can measure the signal which are generated by the controller for the actuation. And also it can connect the output signal of the ECU to loads to simulate the actuators. In case of RCP, it will get the signals from the sensors, and it will generate the signal for the actuators. And also it can receive bus signal which are sent by the other ECU and send bus signals to other ECU. So like in automotive, there are a number of ECU in the vehicles. So like it can simulate also. Now why hardware in loop testing? So it like you can test function in early development stages. Tests are possible in any desired condition. So you can do any like suppose in inverter case you can do the short circuit. You can open loop condition also. So a lot of things you can do it without any safety reason. And the tests are possible under any desired condition. Laboratory test reduce time and cost. Test in failure and other dangerous situation are no risk. The tests are reproducible and can be automated. So like by Python coding or maybe the using the different software like automation test, you can automate every test thing automatically. There is no need to do the manual thing. So like you are going to open this MATLAB. So all the things can be done by using the automation test. Okay. So what is a ScaleXO basically? So it is a modular real-time platform for the hardware in loop testing and for the RCP application. It has the like high performance processor and the FPGA technology, comprehensive, precise and fast IO capabilities and the bus support. Bus support means like CAN, LAN, Ethernet or other communication channels also. So you can see here how the ECU testing has been done. So like this ECU has to be tested. So it will be connected to the different channels of this hypertext of this ScaleXO system, and external loads can be also connected as per requirement. You can use your tester device to check the signals of any on the channels, and this device will be connected using to host PC simply by using the Ethernet. Okay. Okay. So these are the different labels of this Galaxy system, and the size of the system increases as per the requirement. So like in here, you can see that this is can be used. This is the Scalexo system can be used as a desktop version, and it can be done for the signal level hill testing, and this up to this level like up to customized hill, it can be done with the signal level hill, and other things can be done with the power level hill. So the difference between the desktop rack version and the application specific customized hill. So like depends upon the use cases, like how many issue you want to test, what are the different requirement of the issue. So we customize also. Okay. So different tool chain has been used for the hill testing. So like for the user interfaces, different software like configuration desk, control desk, automation desk, model desk, and the motion desk will be used to use this Scalexio hardware. Also to simulate, there is two options here like EOS and the Scalexio. So your model can be simulated either in BIOS in the virtual platform, or either you can run in the real-time system. So like Scalexio system, and their IO can be connected to the ECU control. Okay, so this way it can be done by using the dSPACE toolchain. Okay, so I will explain some of the software and which is required using for the hill testing. So like so the first software is like configuration desk. So this configuration desk will be used for the two purpose basically. First is for the channel assignment, and for those channel their function assignment. Okay, so Simulink FMI virtual EC can be integrated. So Simulink like MATLAB Simulink, you can integrate. FMI is like functional mockup interface. Like there are other software solution simulation software also. They can generate the FMI file that can be integrated to the configuration desk. Also, there is a provision to integrate the virtual issue, and yeah, multimodal capabilities. So you can integrate multiple model, and also for the multi-processor system also, like if you want to integrate some model in one processor, some model in different processor, that is also possible. Better overview, multi-selection. So you can select multiple channel at a time, and you can assign their function at a time also. So you can see here like every channel where it is connected, what is the configuration for those channels, you can see with the configuration desk. Okay. So there is some view of the configuration desk. So here you can see there is a function list. So there are like for the basic IO, maybe the analog input, analog output, digital input, output, register simulation, for the PWM generation, maybe the PWM generator, or you want to generate the multi-channel PWM. So there are number of functions available, and these functions can be assigned to the specific channels. Okay, for us, suppose that like if you want to see the property, you can see it here, and you can change it as per your requirement in the configuration. When you come to the control desk, so like I already discussed, this is for the monitoring and tuning. So it's basically the experiment software and for seamless issue development or the testing, and it perform all the necessary tasks and gives you a single working environment for instrumentation and simulation control. So once your model is developed and you are going to test the function, so control desk will take care of other things also. Okay. So when we talk about the hill testing, so there will be two approach. Either it is the signal level hill or maybe the power level hill. So first I will explain the signal level hill. Yeah, signal level hill. So there is one like use case for the electric motor. So suppose that for simulating electric drivers on the signal level hill, so there is like inverter, there will be motor, and there will be some mechanics in the automotive. So so this is the red line. So this is the controller portion, and you can simulate all the hardware here, like for the inverter, motor, and your vehicle itself and their transmission. So like power stage, electric motor, and the mechanics can be simulated, and controller it can be attached to the specific signal. But here there will be only the signal level, means like it will be ranged to very low voltage and the very low current. So there will be no actual current, like suppose that motor is taking 15 ampere. So you will not get 15 ampere. So it will be scaled down to the voltage like within that, like 10 volt, maybe the to 30 volt, depends about the different system. So this will be the signal level testing. So what are the can be simulated? What are the functions can be simulated in the real-time hardware? So there will be interface. So like digital in, analog out, analog out, or as a feedback, it can take analog or digital input. And you can simulate the PWM measurement, inverter, motor, mechanics, position sensor, or any scaling thing for the sensor. So that will be the signal level. Okay, yeah. So yeah, and when we are going, okay, so that you can see here, for so this portion will be in your ECU. This complete portion like inverter, machine, and the mechanics. If you are going to simulate it, so that will be the signal level. Now, next time, like you are simulating the electric machine and the mechanics, and you have the real inverter. So that can be simulated with the power level here. So yeah. Okay, so for the signal level motor simulation, there will be various advantages like most flexible and scalable approach, most cost efficient approach, no special safety restriction is required, low space and power requirement will be there. So like you can simply connect to a single phase or the three-phase system. And for the hill level signal level testing, you need there will be some requisites. So like you need and like we need internal signals from the ECU. So like for the power electronics control, we need gate driver signal from the controller, and also we need current sensor feedback. And for the like can be given to the controller, or the position sensor feedback that can be given to the controller. So these channels will be accessible, should be accessible from the controller side. Okay. Okay, this is the same slide. Okay. Okay. Now when come to the power level hill, so again the situation will be the same, but till this should be the real, and these portion will be simulated, and these are the functions that can be simulated with the real voltage and current. So like high voltage measurement portion will be there with our power hill, or there will we can simulate the loads or the e-load interface, motor, mechanics, position sensor, and that can be convert the analog input and out digital signal that can be given back to the control. So this will be like power hill. So there will be different advantages. So like this, you can see like in the signal level and the power level, we are doing the almost same testing, but yeah, the voltage and current will be higher. So like what would be the advantages? So higher test depth, the signal level, same interface can be used. So like what are the software using during the signal level? Same software can be used also, and interface will be the same. Just the this inverter part will be with you. There will be no moving part, higher flexibility than dynamo, and lower cost than dynamo. Lower space also required, so it will be the laboratory based. You can do in the tabletop basis. Okay. So now come to the different solution which is required. So like explain everything. So real-time models will be required, simulate anything. So like you need models for the suppose that motor, PMSM, squirrel cage, PLDC, induction motor, synchronous reluctance motor. We have also support. We also support for the multi-phase drives. Different position sensors can be simulated. And for the hardware side, we have cutting edge processor, flexible I/O concept, high performance Xilinx FPGA technology. So we use Xilinx base boards like Kintex based boards. And it has different board like for the Kintex 7, Kintex Ultra Scale or Kintex Ultra Scale Plus Pro. So different boards are available. These are load modules which can be used for the power hill. So like high performance, power parallel operation, and power recovery is also possible with our power level hill testing. And if you want to simulate the battery, so we have battery model also. So like you can configure the different cells with the series and parallel combination. So these are the real-time models or the library, you can say. This is the hardware side, and this is the related to the electronic load modules for the power level here. So this is one figure for the like very large requirements. So like motor and battery emulator, it can go up to 250 kVA, more than 1000 volt, and it can go up to the 600 P. So these are the basically power electronic switch based emulation, and you can test your controller here. There is a one DSO for other measurements. So this is like a system for the power level here. Now we discussed about the different signal level hill, difference between the signal level hill and the power level hill. But when we are going to simulating the real-time model, there will be two possibility. Either we are going to simulate in the processor, and either we are going to simulate in the FPGA. So in the processor side, we can go like in the microsecond. The sample time will go up to the microsecond, but in FPGA it can go up to the nanosecond. So FPGA will give more precise simulation, but yeah, there will be some challenges to develop the model for the FPGA.
हेमंत सर मैं
Yes, sir.
थोड़ा सा मैं इंटरप्ट कर रहा हूँ. If you want 5 minutes break, because 40
Yeah.
हो चुके हैं. So if you want to take break for 5 minutes, then join after 5 minutes.
No issue, sir. In between, if someone want to discuss anything, I am open to that.
Any participant? No issue, sir. Let's go ahead.
Yeah. No, sir, we will wait. We will wait 5 minutes. See, discussion is required, sir, because it's not so like I'm going to in right direction or not.
No, you are in the right direction, because I think these things are a little bit complex. So it takes.
Yeah. So that better to go with the discussion. No
Sure.
issue, no problem.
Hemant sir, we can start now.
Hold a second. Yes, sir. Am I audible?
Yes, sir. Yes, sir.
Yeah, great. So, till now we have discussed different terminology, basically the mill, sill, pill, and the hill also. In hill case, we have discussed about the signal level hill, the power level hill. But for all these things, we have to simulate our plant model or the controller model to the any real-time hardware. When we call the real-time hardware, it may be the processor-based simulation and the FPGA-based simulation. Now I will discuss what is processor-based simulation and what is FPGA-based simulation, when we have to use the processor-based simulation and when we have to use the FPGA-based simulation. So processor-based simulation, okay. A second. Yeah. So we have different solutions. So this is a one Scalexio EMS solution that can be used for the different functionalities. But the like we have a different ASM electric components library. So there will be some library already available through the MATLAB Simulink block set, but we also provide a library for the automotive domain. So automotive domains, like it's not related to the only motor and the controller or like, so we have different parts in the electric like any vehicle. So we provide the engine library also, and related to that, which is not available in the MATLAB Simulink. So like for in case of the electric component and basically I am talking about the ASM electric component library. ASM stands for the automotive simulation model. So there are different PMSM non-linear, BLDC, squirrel cage induction motor, three-phase inverter model. There will be some controller will be also available with the library, so you can implement it. Now you can see here there is a diagram related to the electric drive application. So you can see there is some block sets. So some blue colored, green colored, and the red color, and this blue one. So in case of RCP, this portion will be with the real-time hardware, and you will connect your channels to this RCP system. But connect the system, you need to assign some function. So like for PWM generation, so we use AC motor control library. So like ACMC PWM out, and can use the multi-voltage in and the encoder. But if you are going to work on the hill testing, so these portion will be with you, and we are going to simulate this complete portion. So this is the difference between basically the ACS MCMC based solution and the AMH based solution. Okay, so FPGA based solution, so come with the FPGA technology. Processor, like normally use processor, so I have not explained more. Once but I will discuss more about the FPGA. So what is FPGA? It's a like field programmable gate array, an integrated circuit that consists of internal hardware blocks with user programmable interconnects to customize operation for a specific application. So the interconnects, like, so suppose that this is one FPGA boards. You can see there will be number of custom logic blocks, and it has like a different D flip-flop and other things also. For the programmable, like it's like a programmed by using the SDL code or the Verilog code. There will be some IP blocks for the input-output block sets. So and yeah. A basic FPGA architecture consists of thousands of fundamental elements like CLB blocks, IO blocks, and the other blocks also. So like the capacity of FPGA depends upon the two things, like their clock rate and how much bigger program can be implemented over the FPGA. So like if you want a bigger larger model, so you need a larger number of custom logic blocks. So you can see here, so this is the complete architecture of an FPGA. So you can see these are the custom logic blocks. Their logical operation will be done, or the arithmetic or the mathematical operation will be done. And this programmable interconnect will be connected through the HDL program as per your logic requirement, and these IO can be configured. So you can see here for the CLB blocks. So each CLB block had 2 slices. Each slices consist of 2 lookup tables, 2 carry and control block, and 1 D flip-flop. But when we are discussing or when we are doing the processor-based simulation, we need MATLAB Simulink block libraries or the like other libraries, which is in the C code or the MATLAB code or the S function code. But when you are going to run in something controller or the plant in the FPGA, you need which is like the library which is provided by the Xilinx, because card is from the Xilinx. But it has like over 100 blocks available, and like you can design on very basic way. And also you can see there will be very limited blocks are available. So like over 100 blocks, which is very limited. Suppose that if you want to generate a PWM generation, in the MATLAB Simulink, you can simply get a 1 DC PWM, or you can get repeating sequence and comparing with the constant, it can generate the PWM. But when you are going to use the FPGA based simulation, you have to take a basic block set like counter, and so that you can limit your counter from 0 to something, so that you can generate a repeating sequence or the sawtooth wave, and then you can compare with the constant you can generate it. But this portion will work up to the 10 nanosecond, and in the processor it can go up to the microsecond. So here you can see that these are the different application areas. So if you are going to work with the FPGA based computation or the simulation, so it can go up to the nanosecond to microsecond range. And for the processor based simulation, it can go for up to the microsecond, millisecond to microsecond range. So what will be the like different advantages or the different solutions where like with the FPGA? So FPGA, why it is like better for like faster processing? So FPGA offers parallel computation with low latency and high resolution IO signal processing in the range of nanosecond, while the processor based simulation is like serial computation. Sample times of FPGA-based real-time application can be shifted down to the microsecond to nanosecond range. So their channel is also faster with a very high precision. So when it is required, suppose that you want to work on some controller, or like you want to generate PWM, and your PWM is going like more than 20 kilohertz. So for the 20 kilohertz, your sample time will be the 50 microsecond. But 50 microsecond, you cannot generate a PWM, because for the Nyquist criteria, it should be at least more than 2 times. Even it will be more than 2 times, you can generate a PWM for the up to 50% duty cycle only. But suppose that if you want to generate 51%, so that can't be possible with the processor based simulation, because it will work with the in the microsecond range. So you need FPGA for very high clock rate, so that you can generate very high switching frequency like 300 kilohertz, 400 kilohertz with your own logic. So that can be possible with FPGA based simulation. Also, suppose that you are going to simulate the motor and you want to see the current ripples, and those are like changing very fast manner. So if you want to capture those ripples, you need to implement on the FPGA based simulation. So whenever your sample times require very low, then you should use FPGA. When the lower sample is not required, you can choose only the processor based simulation. So it depends what type of what is the precision required in your case. You have to choose between the FPGA and the processor based simulation. So how it can be done with the dSPACE software? So suppose that previously we discussed about the host PC going to connect with the our dSPACE system. But in case of FPGA, so there will be 2 portions. So one is the processor based simulation, and one will be the FPGA based simulation. So here in this, you can use the MATLAB to simulate to make your model, or in case of the FPGA cards, you can use the Xilinx based library to implement it. Also, you can transfer the signals from the signals or data from processor to FPGA or FPGA to the processor. And you can use any of the IOs from the processor side IO, so that is the fast IO, and for the FPGA side it can be the very fast IO. So like those things which should be simulated in the microsecond or millisecond range, you can simulate in processor, and those portion which require very fast switching or the fast like in the nanosecond, you can run in the FPGA, and signal can be transferred from processor to FPGA and FPGA to processor. So both option is there, and this can be done with the single model approach. So this is the like configuration for the FPGA based implementation or the processor based implementation. So what are the tool chain it will be required? So like for this for the FPGA, you need to high level visual block programming language. So you need AMD British Model Composer library. So these are the library from the British Model Composer. The second thing, you need some library from the dSPACE side so that you can assign the channel. The channel assignment cannot be done with the configuration task here. You have to simply do in the modeling part itself. Also, suppose previously in the slide you have I have shown showcases the modeling using the STL based library. Now, if suppose that if you want to implement your code, that can be also possible. So in that library there is a block set, that is the black box, so where you can run your code and it can be converted into this way. So HTL code integration is also possible. And also suppose that if you want to use the HDL coder, so HDL coder is basically provided by the Simulink model, where you can implement the Simulink based block set for the FPGA. And also there will be some licenses required to convert the Simulink model for the HDL based implementation. So three-way possible. Either you are going to use the AMD based library, either you are going to run your HDL code, or either you are going to use the Simulink block set from the HDL coder that can be implemented in the FPGA. So three possible options are there. Here you can see like different hardware which are the FPGA, and user can design using the AMD library. And for, as per like there will be some solutions also like XSG utils and the XSG AC motor control. So these are the library made by the dSPACE. Suppose that in the ACMC or the XSG electric component, if you want to simulate motor with like in the nanosecond range, you have to make your model using these very basic library. This will be quite difficult or quite challenging. So FPGA will also work on the model based engineering. So we provide different libraries for the FPGA also, like we provide a library for the simulation based implementation. So as we have shown the ASM electric component, so that was the processor based, and these XSG utils and XSG ACMC and the XSG electric component for the FPGA based library. Okay, so there will be some tools required for if you are going to work with the FPGA. So like from the AMD side, we need British ML Enterprise Edition, and maybe the standard edition also. Depends upon the boards, like what boards we are using from the AMD. And we require what is model composer, so that provide library from the AMD. Also we require MathWorks, so like simulation is required, and fixed point designer tool is required for like higher bit size, and there will be HDL coder is optional. If you want to use it, it's okay. If not, it's. And from DSP side, we are like we provide the FPGA block set 1, and there are recommended. So XSG based solutions. So these are the library. You can model it. That's okay. If you cannot model it, like we can provide the model also. So these are the software solutions. If you want to work with the FPGA based. Okay, so this is one testing motor control unit for the signal level with the FPGA. So like we are going to simulate our plant model, using the DS6601 FPGA board, and we are going to use the channel of the DS6651. So these are the numbers of our different boards for the different applications. Okay, these are different libraries related to the motors, motor simulations. Okay, what are the things available? Okay, so these are the different library solutions available related to the FPGA-based implementation. So like XSG electric component, and for interface. So like XSG electric component interface and the XSG utils interface. So this will help you to communicate between the FPGA and the processor, and the processor to FPGA. So these are the libraries available with the XSG electric component. Like these are the sensor simulation for the sensor simulation. These are for the electric machine simulation. So DCM inverter is available. Other basic blocks are also available to integrate with the FPGA. Okay, so these are other solutions. Okay, so with this, I am closing the presentation part, and also I made one model how to do with that. So maybe I can showcase you. Okay, so I have given one example. So like maybe on the top of that. Okay. Yeah, this example. So I have implemented this portion with our newly launched device. So that is MicroLab Box 2. I am simulating all the things, and also along with the controller also in this MicroLab Box 2. So this is my complete model, what I have showcased in the presentation. So this is the distribution side. This is the load connected. So non-linear load is connected. I am switching here from some constant block, and there is a linear load also. Linear lagging load is here, so that is switching after some certain time with the square wave generator. And I am using one statcom for the active power compensation. So I took one remote PC for that portion for real-time implementation. Okay. So this is the configuration disk, as I explained during the presentation. So if you go to the model function, so these are the functions can be implemented with the configuration disk. So there are a lot of functions are there that can be used for the RCP and for the hill level testing. I have added MicroLab Box 2 here. So it has, you can see different more number of channels. So analog in 23 to 24 channels are there. If you click on the analog in 23, you can see their properties. So it can the voltage measurement range is -10 to 10 volt. So whatever the channel you will click, it will show their properties and their assignments. So with MicroLab Box 2, it has 32 ADC channels, 16 DAC channels, 48 digital I/O channel. Apart from that, more differential digital channel is there for the motor-based implementation. If you'll go to the signal chain, okay. So I have one model, so like 3-phase and active power filter, and we have assigned some channel for the suppose that if you want to take some result over the DSO, so these channels has been assigned to measure the voltage and current on the DSO, so that you can take the result and you can put on your research papers. Okay, once everything is completed, you can simply go to the build and you can click on build. It will generate one SDF file that can be loaded to the different software like for the control desk, that is for the monitoring and tuning. You can see here that 3-phase SAPF SDF is loaded here, and here you can see I'm going to click on go online and start measuring. And yeah, you can see the platform. So MicroLab Box 2 is connected here, and we are running this application. And you can see this. This is the voltage. You can monitoring here. This is the load current, which is non-linear, and then this is the compensated source current is there. So like we are reducing the TSD value. Also, we are measuring the turnaround time. So basically, turnaround time is the time how much time it is taking your model to run the one complete execution. So currently it is taking around, you can see the around 6-7 microsecond with this complete model related to the three-phase Suntech power filter. Also the DC link, here you can see the load is changing from the 30 ampere to 38 ampere, and that is by using this control. I can share you over the model. So from here, we are just removing the load, complete load, and so that the load is changing. Okay, hold a second. Yeah. And also, suppose that if we want to switch something like a non-linear load, so maybe currently it is 1. If I will click on 0, the non-linear load will be disconnected here. Okay. So it means we are measuring here and we are tuning here. So tuning means we can change any parameters. And also if you go to control portion, so you can change the control also, like I have added the KP and KI controller, and for the controlling the value. So suppose you can see here, we can increase the KP and KI value, and in that way the response will change of this the DC link voltage. And yeah, TSD, you can see it's coming almost 5%. Maybe we can tune more this model, then we can get less than 5%. But yeah, different. It will depend upon the various parameters. Okay, so this is all from my side. Now I'm ready to take questions, or maybe we can discuss now.
Any questions, sir, from the participants? So let me start, sir. I have a small question. What is the difference between OpenRT and dSPACE?
Okay, sir. So like, yeah, I don't know much about the OpenRT, but I can answer about the dSPACE. The thing is like, as I not as a dSPACE, like I was the dSPACE user, and like at that perspective, maybe I can tell. So OpenRT has promoted their product related to the hill testing, but in the academics, we promoted our product as a rapid control prototyping, because mostly it was used at the RCP. But in case of the hill thing, we will say we are pioneer in industry, not in India, in other country also. And it's like only how they are promoting the thing. Also, maybe we have not good in the hill portion in the academic, because maybe sometimes a user see like our solution as very costlier. But yeah, as a quality wise, we do not compromise.
So what is the cost of installation if you want to have a laboratory of dSPACE here?
Yeah, maybe sir, for that thing we can discuss separately. But yeah, for what hardware I have used here, so like this MicroLab Box 2, I think here MicroLab Box 2, it will cost around 14.5 plus GST. With like all the channels capacity, because sometimes I visited some other academic institution, maybe the OpenRT provided the complete system, but they restrict with a lot of software to use their channels. So with this cost, you can get 32 ADC channels, and 16 DAC channels, and more than 48 digital IO channels.
So this,
and you can see this complete model is running with like 6 microsecond on.
so this plus Simulink, it will be sufficient for.
Not Simulink. Simulink is a third-party software, so you have to check with the MATLAB Simulink.
No, yes, that's what I'm saying. Your lab box plus Simulink will be sufficient for our one laboratory.
Yes, for Simulink side, you can see if when you are going to install the MATLAB Simulink, there will be lot of tools there. Maybe I can show here. Suppose that this is the MATLAB, right? So if you will go to that version, okay. So you can see these are the tools related to the MATLAB Simulink. But most of in case of academic, the institutes purchase most of the tool chain. But in our case, we require four things: MATLAB Coder, Simulink, and Simulink Coder
Okay,
from the MATLAB side.
MATLAB Coder, Simulink, and Simulink Coder will be sufficient for installing dSPACE.
Yeah, actually, MATLAB is required for your model development.
Model development, yes.
And others library are like optional, depends upon your use case. Suppose that if you want to use the CMScape electrical system, so then you can go for it. Otherwise, you guys Simulink will be sufficient to model any of these anything.
Akashdeep, any question? Any question from any participant? If somebody would like to write
Yeah.
Yeah, hello.
Yes.
Yes. Hello, Hemant sir, this side Dr. Rajesh Pindoria from Thapad Institute.
Yes, sir. Yes, sir.
So
We are known
it
to
was
each
a
other.
great presentation. So yes. So it was a great presentation. You covered everything. So from the fundamental to the research level. So I have one question.
Mm.
So this dSPACE library, suppose somebody know about the MATLAB Simulink and somebody don't know about the dSPACE library. So how and how much time it will take to do the simulation in the dSPACE?
Okay. During the discussion, I have told you two approaches, and the processor-based simulation and the FPGA-based simulation. Okay. So processor-based simulation it will not affect much as if you. I think you have already worked previously, so it will taken. There is no extra skill set is required. No new thing you have to learn. But when you are going to use the FPGA-based implementation, so there is two approach. Either you are going to implement your logic by using the basic FPGA block sets, or either you are going to use our library. So from the initial time, maybe you have used the processor-based simulation. We do all the thing over the click mode. Okay, so you have to just click on that. So there is no need to code. You have to just setting thing. So it will not be difficult even if you are going with the FPGA-based simulation, but definitely it will be little more challenging than the processor-based simulation. It will take little more time. Suppose that during the processor-based simulation, when you click on build, maybe you are using the DS1104 and click on the build, it build in like few seconds, right? Maybe in 1 minute max. But if you are going to model in the FPGA, so that also required to build it to generate code to run in the real-time system. So maybe at that time it will take 1 hour or 2 hours, depends upon your implementation also. If something goes wrong, your 2 hour will waste, right? So that with the challenges there. Also with the FPGA-based implementation, you will get very limited library. And so that we have different approach also. So like you can simulate the complete model in the offline mode also. If everything goes correct, you can go for the build so that we can save your time. And most of the things are like click based. But yeah, for FPGA portion, it may take some time. But comparison to the direct implementation of the FPGA card, it will take very less time.
Okay. Okay, good.
Good. dSPACE also, I am involved with the FPGA-based implementation with the industry and with the academic.
Good. Okay. Good. I'm satisfied. Now, one more question. So dSPACE library. So that is a free of cost simulation?
No. So whatever I shown you during the slide. So maybe in the last slide. So for the FPGA-based implementation. So you can see here. If you will see here, the sign is like AMD arrow one, right? So this is sign from the AMD. So they do provide a library, you can use it freely, no problem. But suppose that you can see here the XSG utils and XSG SMC. So background there is a DE. So it's a dSPACE engineering. So for that portion, you need to purchase the specific library. Because previously you have used only this RTI based library, right? So this is
Yes,
not
yes.
RTI based library. This can be integrated with the MATLAB Simulink, and these are the basically AMD based library.
Okay, okay. Good, good. Okay, thank you so much, sir. Thank you.
Yeah, thank you, Rajesh sir.
Any other questions, sir? Amit sir? Jitendra sir? So should we stop, sir?
Yeah, okay, sir.
So I thank Dr. Hemant Saxena for this interesting presentation. We learned a lot of things. And I hope this will be interesting for our participants as well for their research directions. And I request Saxena sir to please submit the presentation so that we can upload it on AICT website for reference of our participants.
Sure, sir.
Thank you. So we'll take leave. Thanks. Thank you all.
Yeah, thank you all. Thank you for the invitation. Thank you.
Thank you, sir.